Hey everybody, welcome to Karst class that isn't actually in Karst class. Appreciate you guys doing this. It sort of keeps us on track while I have to travel for this research project. So as I talked at the end of class, yes, today, that was just today, I was going to originally do two videos, one more about the carbonate geochemistry and one more about the next assignment that you guys have, assignment number 1. But instead I've decided to just sort of put it all together because I think it works that way. So this is what I'm going to talk about in this video. I want to review some of that carbonate geochemistry. I realized we went over it pretty quickly, and it really is a fundamental piece to understanding Karst systems. So that's where we're going to start, and then we'll work through some of the calculations you need for the first assignment. Some we've already talked about in class, and then I'm going to talk about the first assignment specifically. So that's where we are going with this video. Those of you who know the carbonate chemistry really well, you can fast forward. It has that advantage as opposed to class. So feel free to rewatch things or slow down or speed up. You've got lots of options for this one. Okay. So let's start with the basic carbon chemistry. We've been talking about this, all about calcite, that is calcium carbonate being a solid. It reacts with carbonic acid. And when that happens, we create calcium ion and this thing called the bicarbonate ion. And this is the reaction we've been looking at. This is the same reaction I had up in class today. It's really it's more descriptive and a better description of why the limestone dissolves than perhaps just taking limestone and dissolving it into calcium and carbonate. So the question is, where is that H2CO3 from, that carbonic acid? Well, that actually comes mostly from natural systems. So the CO2, whether it's in the atmosphere, wherever it is, reacts with water and it forms this carbonic acid. And this is why rainwater is just a little bit acidic. In fact, in absence of, climate change or acid rain or any of those things, our rainwater should have a pH of about 5.6, so just slightly acidic. And that CO2, a lot of it comes from the atmosphere. In the case of an aquifer or working with a karst system, lots of that CO2 is going to come from the soil zone. So we'll see the breakdown of carbon, particularly because of organic matter and leaf litter, things like that. In the soil zone, the microbes basically compost it, and that generates CO2 in the soil. So when we see elevated carbon in our karst system, it's very often because of the soil zone. So that's where our CO2 comes from, and it's that CO2 reaction that forms the carbonic acid. Okay, so again, we have to ask ourselves, I've been talking about this is carbonate geochemistry. So what is it that makes it carbonate? And when I talk about species, I mean it's a chemical species, typically a dissolved species, but we work with solids as well, and gases as well. In fact, we do in these reactions. And so a carbonate species is one that contains the CO3 group. So it's things like calcite, which is a solid carbonate mineral. We call those carbonate minerals, so that works. And then we have these dissolved species. We have the carbonic acid, we have the bicarbonate. I'm going to include the CO2 in here because it's an integral part of this reaction series. And again, we've got the carbonic acid in two places in this case. So that's what we define as the carbonate species. When I talk about carbonate species, that's what I mean. We also, not in the reactions above, but if I let calcium carbonate just dissolve by itself, not in the presence of carbonic acid, but just by itself in water, I also form CO3, which is another carbonate species. So just working through these, what are they called? Again, we have a carbonate rock, calcium carbonate, which is calcite or rock limestone. H2CO3 is the carbonic acid. HCO3 is bicarbonate, and the CO3 is called the carbonate ion. So those are the different forms we have of carbonates in our system, or different dissolved species of carbonate. So when I consider those together as a group, I refer to those often as dissolved carbonate species or dissolved inorganic carbon. So if I look at a water system and I say, what is the inorganic carbon? By that I mean we're not looking at organic molecules, but we're looking at inorganic molecules. And we can define that DIC as the dissolved inorganic carbon. And the dissolved inorganic carbon is just the sum of all of the carbonate species. So we've got DIC is equal to the concentration of carbonic acid plus bicarbonate plus the carbonate ion. And I put the CO2 there under the H2CO3 because we know the CO2 is what generates H2CO3, which is why I say, well, CO2, we're going to kind of count it in as part of the carbonate system, but when it comes to DIC, I'm only going to count the carbonic acid. So this graph I showed in class today, and it's looking at pH on the X scale, and it says log AI. All that is on the vertical axis is the log of the concentration. So all of these are drawn with the same y-axis in different concentrations. I'm sorry, different species, all plotted on the same y-axis. So on this graph, what do we have? So let's look at these carbonate species. The first one is the carbonic acid. And notice the carbonic acid is the dominant species at low pHs, and then it tails off as the pH goes higher. The bicarbonate, here in yellow, is the dominant species at the middle of the pH range. And the CO3, the carbonate ion, is the species that dominates at high pHs. Now, there's different ways we can think about this, and one is if I am at very low pH, there's lots of hydrogen present, and we've got hydrogen also graphed on here. So if I have lots of hydrogen, I've got lots of hydrogen available to basically stick onto that CO3 ion. On the other hand, at high pH, there's very little hydrogen. You can picture this hydrogen line keep coming down till it's very, very, very low concentration at a high pH. So at a high pH, there's so little hydrogen present, there isn't much available to put on the carbonate ion. Or you can think of it as, well, any hydrogen there would get stripped off the CO3. Okay, so we've got this range of these three carbonate species, and which one we have depends on what the pH is. So, what about DIC on this graph? Well, the DIC is a horizontal line. So in this case, the total concentration, the DIC, is equal to 10 to the minus 2. And that is constant regardless of pH. So the DIC is constant with pH, but the individual species that are present sort of shift in their dominance and which one is there at the highest concentration. Okay, so this is a graph we're going to come back to a bunch of times this semester. It's sort of one of those fundamental understandings in this system. This table gives you all the reactions we've been talking about and a bunch of the reactions we're going to continue talking about. So the reactions on the left, and I've given you the K values, the pK. Remember, the pK is the negative log of the K. So if the log of K is 10 to the minus 1.47, the pK of that is 1.47. And I've also given you some words that say what I call that reaction. Well, it's not just me. What everybody calls those reactions. So the first one is hydrolysis of CO2, and then the next two are the first and second dissociations of carbonic acid. And an acid dissociation is just the loss of a proton or loss of a hydrogen. So that first step, the first dissociation, is loss of the first hydrogen. The second dissociation is loss of a second hydrogen. We have a couple dissolution reactions, and we have our reaction for the dissociation of water. Okay, so another way I want you to think about this figure a little bit is kind of how the carbon's coming into the system. So there are two possibilities where I can get DIC or some sort of carbonate species into my system. And the first is the reaction of CO2 and water, which is happening way down at a very low pH, where CO2 and water form this H2CO3. So if that's the reaction that's really dominant, I'm forcing H2CO3 in the system, and you can think of it as I'm sort of feeding this figure from the left. I'm feeding it with a low pH. At the other end of the spectrum, we have calcium carbonate, any carbonate mineral, so dolomite would work here just fine as well. And when those rocks dissolve, they generate CO3. And you can think of that as I'm feeding the diagram from the right side because I'm feeding in CO3. What happens in natural systems is both of these reactions happen, and what we find is ultimately our system is sort of an averaging of those two processes, which is why we end up with common pH range in nature is in between those. So what we see, a couple of things to point out here. One, think about this. I've got CO2 feeding in H2CO3. I've got rocks feeding in CO3. The average between those is going to be some here in the middle line. The dominant species in most waters is going to be HCO3. That's true of pretty much all carbonate waters, because carbonate waters fit nicely into this area. So just keep in mind that the most important carbonate water from the standpoint of just what's present at the highest concentration in a carbonate system is almost always HCO3 or bicarbonate. And that's because most natural waters are in that circumneutral pH range. Okay, a bunch of definitions here. I'm going to go through these pretty quickly because you have them defined here in front of you, but I want to make sure we're clear on these. Alkalinity is actually defined in a number of different ways, but the easiest way is it's the measure of a solution. That says to neutralize pH. That's incorrect. It's to neutralize an acid. So while you're watching, we're going to correct that right here because we want to make sure it's correct. So it's the measure of a solution to neutralize an acid. Very good. Excuse me. A pH buffer is a solution that sort of maintains a constant pH, like an add acid or base to it, remove acid or base, and that system maintains a constant pH. So that's referred to as a buffer. And a buffer, when we want to measure the buffer, that's referred to as a buffer capacity, of how strong or what the measure of the buffer is. Carbonate waters, because alkalinity is dominant. So alkalinity is effectively, go back, let me pull up a pen. Okay, pen in here. Okay, so alkalinity is, what creates alkalinity in our system is basically HCO3. So alkalinity and HCO3 are almost the same, which means in a carbonate water, and where we have a lot of HCO3 present because of the rocks dissolving, means that we have a lot of alkalinity typically. So carbonate waters are very well buffered. And in almost all natural waters, if there is a strong buffer to the natural water, it's almost always a carbonate. The units of alkalinity are a little bit odd. I'm not going to go into the conventions in this class as far as how we get these units, but alkalinity is basically a charge measurement, and it's measuring the moles of charge, which is what is an equivalent, or milliequivalent if we're thinking about milli terms. So I've given you 4 numbers here. These are the same concentrations. So 1 milliequivalent per liter of alkalinity is the same as 1 millimole of liter of bicarbonate. So they're basically the same thing. I'm making the assumption that this is bicarbonate. I can convert that into other units, such as bicarbonate, or very often alkalinity is reported as milligrams per liter as calcium carbonate. That is, we're not saying it's really calcium carbonate, but those are handy units. And so you can, those 4 bullet numbers right there, you can treat as conversion factors between these different units, and you can use those all semester. Some of the things we want to calculate in a carbonate water system, because they're going to tell us about the source of water, they might tell us something about what's going on with the chemistry. Why we calculate each of these, we'll work our way through. But the 3 I'm going to talk about here in this talk. One is the PCO2, which is a hypothetical partial pressure CO2 in contact with the water sample. Sometimes we express that as an ePCO2. And saturation indices. So a saturation index has to do with how close we are to equilibrium with a mineral. And in this case, we're going to do calcite and dolomite. Saturation indices are always, always, always with respect to a specific mineral. Okay, so first let's start with this PCO2. So let's say we want to estimate the PCO2 in association with our water samples. That is, how much partial pressure of carbon dioxide would we predict is in equilibrium with our water sample. Well, we can back calculate that doing some playing around with the chemistry and the mathematics a little bit. And I did this in class, but I decided in this presentation, instead of going through the derivation and the math, I'm just going to sort of give you the equations. You have good resources in eCampus and on the Google Drive to help you out with these sort of things. Your textbook has good information on how to do all these calculations. Chapter 5 from Will White's textbook is also posted, and it also has this kind of information. So you've got it in various places, and you have it in this talk. Okay, so PCO2, what do we want to calculate? That partial pressure of CO2 is calculated in terms of atmospheres. ATM is atmosphere. That's a unit of pressure. The bicarbonate concentration is in moles per liter. As when we work with brackets, they're going to be in moles per liter. And any kind of theoretical equation and calculation is going to be in terms of moles per liter. In this case, we're going to make life simple and just assume that the alkalinity is bicarbonate. K1 is the first association for H2CO3, and the KCO2 is the Henry's law constant for CO2, which is the hydrolysis of water. So K1 and K2, those are constants for 2 different chemical reactions, and they are thermodynamic constants. They don't vary a lot. They vary a little bit with temperature, but it's minor. And we're not going to worry about that this semester. So those are values you're just going to go to a table and pull. So you've got K1, you've got KCO2. They're givens. Well, if you have a water sample, we very, very often have pH. We very often have alkalinity, which means you can estimate this value of PCO2 very readily from water chemistry. In fact, that's what you'll end up doing in this problem set. Log PCO2 is often a good way to report CO2. So the CO2 number you're going to get is going to be something like 10 to the minus 2.7, which isn't really all that helpful a number as far as intuitively understanding what it means. So we're typically going to report these as a log value. So the atmospheric background, that is the concentration of CO2 in the atmosphere before climate change really got going, is 10 to the minus 3.5 atmospheres. So the log PCO2 in the atmosphere is minus 3.5. We also use this value of ePCO2, and that refers to excess PCO2 or enhanced PCO2. It's not electronic, it's excess or enhanced. And all it is a ratio. So it's the ratio of the CO2 you calculate for a single sample divided by the atmospheric equilibrium. So this number in the denominator in my math, pull the right one, there, the CO2 is directly from the line above, and that is the atmospheric equilibrium. So why is this helpful? Well, I can tell you, oh gosh, the PCO2 concentration is 10 to the minus 2.5. And it's hard to hear a number like that and really have an intuitive understanding what it means. But instead, if I told you that the CO2 in the water is 10 times greater than I would expect based purely on the atmospheric input, well, that seems to have a lot of meaning, and that's an easier number to kind of tag your understanding on. So that's why we're collecting or why we calculate ePCO2. It just gives you a nice ratio. How much is the CO2 enhanced above what I would expect purely based on the atmosphere? So to give you an idea, a lot of surface waters might be enhanced 10 times more than the atmosphere, or maybe 50 times more. A karst spring might be enhanced 100 times more than atmospheric equilibrium. On the other hand, we also do a very similar thing with mine waters, with acid mine drainage. And we have some sites, it's 1,000 times greater CO2 in the water than you would expect at equilibrium with the atmosphere. So that's why we calculate ePCO2, is it provides a really kind of easy way of thinking about what the number means. Okay, so this is a graph. Again, I showed this in class today. On the y-axis, we have partial pressure of CO2, and that is in units of atmospheres. That's not on there, I don't know why. Calcium is a millimole per liter, or millimolar, and we're using calcium as a measure of how soluble calcite is. So because calcium is a nice product of our chemical reaction, that allows us to use that calcium as a measure of how much of the solid is dissolved. This curve is the solubility plot for calcite. So anytime we're on that curve, we're at equilibrium. So this is a graph we're going to use a bunch this semester, and let's think about what this means. So let's just, to start, I put a vertical line on mine at minus 3.5. Well, that is the amount of PCO2, or the concentration partial pressure. A partial pressure is effectively a concentration for a gas. It's how we measure the concentration and the density of a gas phase. Okay, so our partial pressure of CO2 is minus 3.5. That is atmospheric value. If I have that PCO2 in contact with calcite, what happens? Well, that's how much calcium I would expect to see at equilibrium. That is, it's about, 0.5 millimolar calcium is the equilibrium solubility of calcite at atmospheric CO2. I could do this also at a higher PCO2. So here I'm at minus 1.5 for my log PCO2. And at that PCO2, I would have quite a bit more calcium in water. So now my calcium is more like 2.6, 2.7, something like that. So a couple things we want to note from this graph. One is that line gives us the equilibrium. Okay, it defines the equilibrium where that chemical reaction is going in both directions at the equal amounts, and so I don't have a net gain in either direction. So equilibrium is a nice, easy place to sort of start looking at the chemistry. Another thing I want to point out about this graph is as the PCO2 increases, which it's increasing from left to right, when it increases, calcite is much more soluble, and it turns out that the solubility of calcite in limestone is driven primarily from CO2. And that's what we see in this graph. This is not a linear relationship. This is actually a cubic term on this function. You can't tell that by looking at it. I just happen to know the function here. Okay, so what else on this? Notice here, when we go from this is the log graph. So when I go from -2 to -3, that is 1 log unit. That means things have changed by an order of 10, right? Because logs are orders of 10. Which means when I go from -1 to -3.5, I have changed my value by 100 times. So it's 2 log units, so it's 10 times 10. So the difference between the two examples I gave you is 100 times difference in my atmospheric concentration of CO2. Okay, so when we are on the line, we are at equilibrium. Again, nothing's changing. Remember, one of the questions we've had from day one is the reaction going to the left? Is the reaction going to the right? That is, if it's going, the reaction's going to the right, maybe I'm forming caves. If the reaction's going to the left, maybe I'm decorating caves or depositing limestone. On the line, there's no net gain either way. We're just at equilibrium, and they're balanced based on the cave for this chemical reaction. Okay, but we're not always at equilibrium. Equilibrium chemistry is a nice place to do chemistry because it's very straightforward, and it's where we always start to answer a question. But the truth is, systems are often not at equilibrium. They're somewhere off of that. So the question is, if we're not at equilibrium, which way are we? How does the direction go? There are a couple different ways to calculate this, but in this class we're going to work with saturation indices, which is the traditional way people work with us in Karst systems. So let's consider this point here. We have a little blue dot and it's above the line. So we're not at equilibrium. We know that because we're not on the line, and the line defines equilibrium. But what's going on here? How does that happen? Well, first of all, maybe I don't just have calcite solution. Maybe I also have gypsum, and the gypsum, not Egyptian, but gypsum, has also released calcium. So I can have calcium from a completely unrelated source in my solution, as well as calcium from calcite. In this graph, though, if you look at this PCO2, so we're -4 PCO2, which we wouldn't really see in a natural system. So this is more of a hypothetical example. If we had a PCO2 less than atmospheric, then we solve climate change. But for the case of our example, we have a symbol, and it's above the line. Now that means at this PCO2, the amount of calcium I would expect in my system is down there like 0.2 or 0.3. I have a lot more calcium than that. So my system has more calcium in it than what I could get from calcite at this PCO2. So what does that mean? Well, then I would call this solution oversaturated or supersaturated with respect to calcite. That is, there is more calcium present in my solution than I could expect at equilibrium. Therefore, we call that oversaturated or supersaturated. The other scenario we could have here is this little red square. So the little red square is beneath the line. So now we have sort of the opposite case where at that PCO2, I would expect there to be more calcium in solution than what we actually have. So this sample we could call undersaturated. In the US, we almost always call it undersaturated. In Britain, it's referred to as aggressive. And I like that term because this water is aggressive. That is, it can dissolve water. So if I'm above the line, I have too much calcium to allow calcite to dissolve. I'm oversaturated. Well, if that's the case, then maybe I could precipitate calcite, and that could happen. It's oversaturated. That is, there's too many products for what we expect to see in our chemical reaction. So I'm going to drive my reaction back to the left. In our case, the red example here with the undersaturated, that water, there's not that much calcium in my water. So my water has the capacity to dissolve more calcite. So it's undersaturated. I like the term of aggressive because it can aggressively attack the rock. Okay, so we can sort of think about this conceptually and see it on a figure. The question is then, how do we do this mathematically in a way we can actually calculate it? Because I want to know, not just am I oversaturated at equilibrium or undersaturated, I want to know how far I am from equilibrium. Because it turns out dissolution happens better the further I am from equilibrium. Okay, so to do this, we're going to use something called a saturation index. So the saturation indices are what tell us whether we're over, under, or at saturation. They're always with respect to a specific mineral. So you can calculate these. You can take a water sample and calculate it for 80 possible minerals that could have participated in that water. So a saturation index, which is called an SI, and it's given a sub little x there because it's mineral X. We will put C for calcite, D for dolomite. It's equal to the log of this ratio, in which in the numerator we have, it's sometimes called the ion activity product. I've just called it the ion product here. And below is the equilibrium product. That is the K value for the equation. Okay, I think it's more helpful to see a real example. So let's look at calcite. So if that's our reaction for calcite, the saturation index with respect to calcite is equal to the log of the calcium times the calcium concentration times the carbonate concentration divided by the Kc, where the Kc is the equilibrium constant for the reaction above. So here's one way you want to think about this. In the numerator, that looks like how if we drew out the Kc, what it would look like. So what's the difference? This value is what's in the sample. So if you measure a water sample and you say, well, where do I put this? Well, those are the concentrations that are about what is actually there. I'm making no assumption about equilibrium in the numerator. The denominator assumes equilibrium. It's the thermodynamic value for equilibrium. So you can think about this. It's a ratio of what's actually there divided by what we predict would be there. We can rearrange this a little bit. Again, I'm not going to go through the derivation of this. If someone wants to see it, I'm always happy to do this. Come to office hours and we'll whip this baby up. But we can define this in terms of things we can easily measure. So the saturation index for calcite is equal to the log. Notice the K2 and the Kc are thermodynamic constants you get from your table. The calcium concentration you would have measured, so that would be tabulated. The bicarbonate, which we're assuming is the alkalinity, but it's typically given as the bicarbonate concentration. And we're going to divide that by 10 to the minus pH. 10 to the minus pH is the same as the concentration of the hydrogen. So if the pH is equal to the negative log of the hydrogen concentration, then the hydrogen concentration must be equal to 10 to the minus pH. And I bet you can work that out if that's not immediately intuitive. I can also rearrange this in log format. In the Ford and Williams textbook, they do this for you. So you can look at how they've done this. And I've just taken the log, or the saturation index for calcite, and I've broken out that fraction part of the calculation in the log form. So it's the log of K2 plus the log of calcium plus the log of the bicarbonate minus the log of the Kc, because it's in the denominator, plus the pH. The pH, it's the log of the minus 10 to the minus pH, which is how we get a positive pH. But anyway, that's the log form if you find that easier to work with. So we can do the same thing for dolomite. Dolomite's a little bit more complicated than calcite because I've got two carbonates in my chemical reaction, which means that I do need to square the concentration of the CO3 when I set up my mass action equation or my equilibrium expression. So let me go back. This upper part, ion product, is what we have to square, and you would do that just like the K. So that's a squared term because of the stoichiometric coefficient of the CO3. So that's part of that ion activity product or ion product. And of course Kd now, because now we're looking at the solubility of dolomite, so I need the dissolution value for that reaction in the denominator. Okay, this one we can also rearrange it so it's in things we can measure more readily. So now what the things that we've changed here, I don't think I showed you what changed. So let's look, if we look at this equation, CO3 is hard to get. So Kd is a set value, calcium concentration we get, Mg concentration we get with laboratory work. But CO3 is hard to measure. So the way we do this is we convert the CO3 into the bicarbonate concentration. And in doing that, I have to bring in that K2, and I have to bring in the hydrogen and the pH. Again, you don't need to worry too much about the form of this or how we get to this. You just need to be able to use this And we'll spend some time, more time, as we move forward, talking about what this all means. Okay, so these saturation indices, let's come back to this graph, and this is the graph of calcite solubility. So I want to look at what would the saturation index be in these different conditions. Now the easiest one here is the equilibrium one. So when we are at equilibrium, the value would be 1. Remember, it's just the ratio of what's there to what we think should be there at equilibrium. And if what's there is what we expect to be at equilibrium, we're at equilibrium, the value comes to, the ratio is 1 and the saturation index is 0. So when I'm oversaturated, it means I have more products than I would expect, which means that ratio must be greater than 1 and the saturation index must be greater than 0. So we start when we're oversaturated, we're greater than 0. I already said at equilibrium, we're equal to 0. And undersaturated, we're less than 0. Why is that not 1? Because these are log terms. So if we come back up here, I say we are at, let me come to a good one that works. When I am at equilibrium, the value I expect to be there, this one, is the same as what we are at equilibrium, which means I've got the log of 1, and the log of 1 is equal to 0. That's why we're looking at 0 as our line of above and below equilibrium when we look at saturation indices. Okay, so that gives us that value. So again, thinking about what does that mean about the direction the reaction goes, which is really the question we've been trying to get at to start with. When we're oversaturated, it means there's too much calcium present for what we would expect at equilibrium, which means the reaction is going to go from right to the left. We will precipitate calcite, or precipitate the mineral, whenever we're oversaturated. Okay? At equilibrium, nothing happens. The reaction goes equally in both directions. And when I'm undersaturated, my reaction goes from left to right. That is, I'm able to dissolve more calcite, and that's because my water is capable of accepting more calcium, and so therefore I can dissolve more calcite. So these values, that whole question of which way is that direction going, this gives us a way to answer that. You know, if I look at a water, is this water dissolving caves, or is this water precipitating stalactites back there in our cave? Okay, so it'll give us a way to quantify that. Okay, so that's what I wanted to say about some of the geochemistry. And I wanted to cover particularly the PCO2 and the saturation indices for the sake of how you do those calculations. This is what the assignment looks like. If you have a look at it, it's all available on eCampus. There's a folder there with both this information and resources as well. So the first thing you need to do is you do need to read the problem set guidelines. Those are also posted in the resources. So that's sort of how we go about different things in this class, how to lay out problems to do them right, how to submit your problem set when you have it done. And all of those are there. One of the things you're going to do after you read those is just a little quiz on eCampus that gives you your AMP points for having done that. So there's a few questions about how do you submit things, kind of thing. The other thing I ask you a question about that I think is important is this idea of graphs. And I've given you some different formats of graphs here. And I just want to walk through when you would use different ones. I think especially when you haven't created a lot of graphs, or you're really just digging into data sets as a scientist, people just sort of make a graph and don't necessarily make a deliberate choice about what should be on the graph, whether it's symbols or lines or that kind of thing. So I wanted to show you some different formats and talk about when you might use different ones. So I just want to go through these. I realize they're kind of out of order because I added another one late. A is just symbols. No lines, no anything else, just data. So we use symbols when we have truly measured data, not predictions, but just real stuff. And sometimes we just want to plot the data to explore the data to see what it looks like. So that's the first thing I might do, and that would be figure A. In figure B, I have the same data set, and I've put a best fit line through it. Excel will call this a trend line. It is actually a linear regression from a statistical standpoint. And the things that are plotted up there, y equals mx plus b is the equation of that line. and an R-squared, which tells us about the goodness of the fit. R-squareds go from 0 to 1, with the higher numbers being a better fit of the data. What exactly makes a good R-squared depends on how many data points you have, but usually the higher, well, always the higher the R-squared is, the better the fit. Whether it's statistically significant depends on some other things. One of the things I would caution you about, it's very easy in Excel to put a trend line through. But this trend line assumes it's a linear relationship. And sometimes they're not linear relationships. And there's no reason to expect a linear relationship. In that case, I would argue that a linear plot is not a good one. Sometimes, maybe I measure the same variable, variable A and variable B. But I measure variable A, but two different ways. They should be the same. So I might plot variable A measured one way on the x-axis and variable A measured a different way on the y-axis to see, are they really the same? In that case, I don't want a linear regression. I want a line, what we call a parity line, that is, it has a slope of 1, that shows an exact match between those two different measurements. So if the two measurements are supposed to be exactly the same, you don't want to put a trend line through it, you want to put a parity line through it. So although trend lines are easy, we need to be a little careful when we choose them. Figure C has the data, but it's offset from that line. The time we would use that most often is when there's some sort of a theoretical value, that is, the line defines a theoretical function, and the symbols tell us something about how the real data fit relative to that. A good example of that will be the one we just did of the calcite equilibrium that had that curve, and it was, in fact, a theoretical relationship for the solubility of calcite. And I gave you a couple data points, a little triangle and a little square, and said, well, what if our data were like this? So comparing the data to a theoretical line to better understand to what extent does that theory govern your data. Can you predict the data based on the theory? So that's what C is. That's some other reason that line is there. My example of a parity line, that is a slope of 1, would also work just fine in this. This is clearly not a parity line. That's a slope well off of 1. But you could use a parity line graph might look this way. D is a connect the dots. We as scientists don't really want to connect dots. It's not a good habit. So why would we do it sometimes? The one time that we do connect dots and symbols is when we have a time series. We want to show progression through time, and it's much easier to see that progression if we do connect the dots. Sometimes in some graphs, when people do it, they might even add a comment of line provided to aid the eye. That is it. I've made it easier for you to see the trends in the data by adding the line. But generally, we don't do that. If the data are very, very closely spaced, I might not use the symbols. I might just use the line. So for example, we have data logger data for 5 years at 5-minute intervals. Well, if I put the symbols on that, you'll never be able to see the line. So that's when you would use a line. I'm sorry, you would use just a line and not the symbols. E is just a theoretical function. If you have a theoretical function, don't put symbols on it. That is from mathematical definitions, I would call that a continuous function, because for every value of x, there is a value of y. So any points I would put on that to define it would be arbitrary. I could pick any value of x and I would still get a value of y. So that's what figure E is. And this is the kind of thing I look for, and we look for when we create graphs, because this class is also about communicating science. So many of our classes are, and making sure you make thoughtful decisions on your graphs is really important. Okay, so what are you actually calculating in this problem set? Well, the data set that you're using comes from a paper by Schuster and White, and I've pulled data from 2 locations for you to graph. However, for one data point, just one data point, you're going to do some hand calculations. So I'm going to have you run through these. We have some unit conversions of moles per liter, molar units, hardness, and ionic strength. I talked about these in class today, so you'll have the equations from class. And again, use your resources from your resource file. Use Ford and Williams, use Will White's book, and they will also give you equations for how to calculate all these. The ones I've been talking about today, I talked about PCO2 a little bit in class today, and I've talked about it some more today. So ePCO2 and saturation indices are things you're going to calculate as well. And those are all in this talk. You've got the equations. Again, your best choice when you want to look up an equation, I would look it up in your textbook and not just go to your notes, especially if they're notes you've taken in class. Because when they go from me writing down something in my notes, me putting it from my notes to the board, you getting it from the board to your notes, there's just a lot of steps that can cause error. So I recommend you go to the textbook and double check the equations there. Okay, so after you do this calculation, so you're going to do a hand calculation for one sample. Then what you can do is we want to see if it's any good. It's really, as scientists, it's one thing to be able to calculate something. It's another thing to know whether your calculation is correct. To have some sort of a measure of, am I in the ballpark? Does this make any sense at all? And we like to stop and look at that with our calculations whenever we do a series of calculations. And I call this a sniff test. Is it stinky or does it pass the sniff test? So here are some of the values you've calculated. What you're going to do is go to the original paper where these were published and see if your numbers match reasonably well to theirs. So they're out of this paper by Evan Schuster and Will White. This is actually one of the papers we're going to read for our in-class reading at the end of the semester. So this one you'll see again. But you're going to have to look at the graphs in that paper and get an estimate of what ratios they used for those locations. And see, do your numbers, are they in the ballpark? Do they pass the sniff test? So this is how you're going to do the sniff test on this data set. You're going to create some graphs. So based on the raw data you have, you're going to graph a number of things through time. How do things change through time? So there's two locations, and there's a time series for both locations. So what you'll do is create a graph with time on the x-axis. You're going to put both locations on the same graph so you can see the temperatures side by side. You'll be able to see the calcium side by side. So you end up creating a total of 4 graphs for that. Please check the problem set guidelines about what graphs work and what graphs don't, and please be thoughtful in your choice of how you design your graph. Okay, so we started with some hand calculations, we've got our graphical analysis, then we're going to do some Excel calculations. So all of those parameters that you were hand calculating back here in number 1, you're going to do for your entire spreadsheet in number 4. Now that means you're going to have to write the equations in Excel and have Excel do the work for you. This is too many numbers for you to try to do by hand. It's very quick to do in Excel once you figure out what you need to do with the math. So these are the parameters. It's the same one that was on the hand calculations. I think I added a couple more here because they were easy to do. So again, do that. You need to take your hand calculation and check it against this. That's sort of your internal sniff check of, is your calculation correct? Does your calculation match what you want it to do? Or does your spreadsheet match? If you're not used to writing equations and spreadsheets, talk to me, talk to classmates, go to the YouTube channel that I've set up for you guys, and there'll be lots of help to do that. But you do not want to calculate these all by hand. If you try to do that, you'll just never get through this problem set. The last thing you're going to do here, number 6, is to calculate just some really basic statistics. Again, you're going to use Excel, calculate the average, the standard deviation, and an RSD. And RSD, it's defined on the problem set itself. It's a relative standard deviation. It's just the standard deviation divided by the average multiplied by 100. So if my average value, it allows us to compare numbers when the average values are very, very different because it normalizes out the average. So you want to do all of these in Excel. You want to do these calculations in Excel as well. And again, it will make your life a little easier. Okay, so you need some resources to do all this. Here's what you've got. On eCampus, in the assignments folder, the assignment itself in Word, and you can pull it down in Word because you're going to need to paste in all of your graphs and little pieces of your tables, and that information on how to do that is on the problem set guideline, which is also in that same folder. The data set you'll be using for this is in that folder. The table of thermodynamic values with the equations is in the folder in the paper by Schuster White, which you need for your sniff test. The other resources that might be helpful, I think they're on eCampus or in Google or possibly both at this point. The Ford and Williams, Chapter 3 is helpful. Will White, Chapter 5, which is all about how to do these kind of calculations and what they mean, Oh, good. However, do not use the chemical equation for dolomite saturation index from Will White. That one, he uses a different form of the chemical equation for dolomite, and so his calculation's a little bit different. It's correct. It's just different than what we've been doing. And also make use of that playlist on YouTube. If you've never written an equation in Excel, go to that YouTube playlist and that'll help you out. So if you have questions, we've got lots of resources there. Go have a look at those, see if that helps. Of course, as you know, you're welcome to talk to your classmates, particularly like, do you know how to write an equation in Excel? That's totally okay to talk about that kind of stuff. You do have to do your own work, do your own calculations, and turn in your own work when it comes down to that. But it's totally fine to ask people about how to do skill things, and that's a good thing to do, to reach out. Also, you can ask me. I have office hours, I have email. I realize I'm away the next few days, but I will be back on Sunday and happy to help with that kind of thing. But hopefully if you've got some Excel skills, this should be pretty straightforward. And if you don't, ask around first, and my guess is you'll sort it out before you ever need me. But I'm here if you need me. Okay, this has sort of been a whirlwind tour, but I figured I could go pretty quick because you guys can go back to the extent you need to. I think this puts you in a position to really dive into the first assignment, and I encourage you to do that. I will be happy to answer questions at the start of class on Tuesday if people have questions on the problem set. I would recommend not putting this off till the last minute. I know that's always sort of appealing, but if you get caught and you discover you don't know how to do something in the Excel at the last minute, you're going to have a hard time getting this done on time. So have a look. As I did explain in class today, I just mentioned again, I've broken this sort of analysis into two parts. I realize this is a lot of calculations without a lot of what's the interpretation, what does it mean. And I decided to split that into two problem sets. So this one, we're actually just working on generating the numbers we need. In the next problem set, you're going to work on interpreting the numbers from this problem set. And part of the reason I've done that is if I put them together, what I find is if anyone struggles and you can't get the right answer numerically, then the interpretation is sort of not a good use of your time because you're trying to interpret numbers that are wrong. And it can be misleading, or it can just, you get confused because it doesn't make sense. And that's not particularly helpful. So I figured this time what we're going to try is you'll do the calculations first, and then we can get those ironed out, which puts us in the perfect position to actually interpret the data. So that's where we are. And again, please give me a shout if you have questions. But otherwise, have a great week. I will see all of you next Tuesday. I'm going to assume you've all watched this prior to next Tuesday, so we can just go forward. I'm sure you will. I mean, what else do you have to do on a weekend? Anyway, have a great weekend, folks, and I'll see you later.